Okay, so today we're going to talk a little bit about calorimetry. And you can see the definition here on the screen. Calorimetry is the measure of heat flow. And we'll be looking at a pretty simple example of this. So we're going to be doing something called coffee cup calorimetry. And you can see from this diagram I have over here that we just have basically a styrofoam cup that's going to be full of water with a thermometer in it. And this apparatus as a whole is going to be called the calorimeter. Now, what we can do with this is actually pretty interesting considering it's a very cheap piece of equipment. So what we could do is we could take a metal and we could heat it to a known temperature. So let's say we take this metal cube and we heat it up to a temperature like 100 degrees Celsius. We take that metal and we drop it in the calorimeter. Now, this water at the beginning of this setup would have probably just been at room temperature. So we'll say this water is at about 20 degrees Celsius or so. And this metal that we dropped in, we had heated it up to a much warmer temperature than room temperature. So we said something like 100 degrees Celsius. If you drop this in here, obviously the metal is going to be much hotter than the water. And we had learned in previous videos that heat will always flow from a hotter object to a colder object. So what's going to happen when this hot metal gets dropped in the calorimeter, it's going to cause heat to flow to the water. So what's going to happen basically is the heat from this metal is going to be transferred to the water around it. And we can actually calculate the amount of heat that is dispersed from the metal to the water by using an equation, which we had talked about in the past, which is Q equals mc delta T, which we're going to see next on the example you're going to see. But we can measure how the water's temperature changes, and we can do some basic math to do a calculation. So let's actually look at a situation or a word problem, and let's put this to the test and see what happens. So right here, we're basically looking at a pretty common example you might see. So again, we have a metal. Now, we're not told what element this is or what type of metal it is, but we'll get to that part a little later. But we have a piece of metal, we're given its mass, and we're told it's heated to 100 degrees Celsius. It is then put into 100 milliliters of water, and we're told the water's temperature in this case is 23.7 degrees Celsius. Then it goes on to state that the metal and the water were allowed to come to an equilibrium temperature. So this part can be a little confusing what this means. An equilibrium temperature means nothing more that the metal and the water at the end of this problem or experiment have the same temperature. So we're then told that this equilibrium temperature is 27.8 degrees Celsius. We're assuming that no heat is lost to the environment. Now, this is a pretty big assumption, but this is done a lot in problems like this. In real life, there's always going to be heat lost from the calorimeter and to the surroundings, to the environment outside of the calorimeter, but most problems assume that no heat is lost. Now, the whole purpose of this problem is going to be to determine the specific heat of the metal. So this is a very long word problem, and this can look a little intimidating to a lot of students when they first see things like this, but it's really not that bad. So what are we going to do first? Well, we're going to use an equation, Q equals mc delta T. And we're going to use this equation actually twice, but the first thing we're going to do is try to figure out the amount of heat that the water absorbs. So remember, this metal, we are told, is very warm. So it was 100 degrees Celsius, and the water, by contrast, is much colder. So we know that this metal at 100 degrees Celsius has to transfer its heat to this colder object, this colder substance, which in this case is the water. Some key things that you're going to have to know, which are not mentioned, is this little part I have down here that I'm highlighting. 1 milliliter of water is equal to 1 gram of water. This is not true for every chemical, but in this case it's true for water. So every 1 milliliter of water weighs roughly 1 gram. So we're going to carry on through this question. And what I like to do first is just to jot down the equation that I'm using. So you can see I've got my Q equals mc delta T. And then what I really like to do is kind of take an inventory list of everything. So some things I'm looking at here, the whole purpose of the problem is going to be to solve for Q for this first step. And I know the mass of the water because if 1 milliliter of water equals 1 gram, then 100 milliliters of water will equal 100 grams. The specific heat of water is a pretty common number that you're going to use a lot. It's not given in this problem, but it's 4.186, and that's just something you could look up online or in a textbook, but this is a number you'll really want to get familiar with because water is going to be used in almost every calorimeter. Now, delta T gets a little bit complicated. This is the change in temperature. So as we're looking at these variables, Q is the heat that the water absorbs, M is the mass of the water, C is the specific heat of the water, and delta T is the temperature change of the water. So how did I get this number here of 4.1? Well, what I did was I looked at the problem and I saw that initially the water was at 23.7, and then the equilibrium temperature in this case is 27.8. So the final temperature, 27.8, minus the initial temperature, 23.7, that's what actually got me this 4.1 number, or the delta T, or change in T, change in temperature. Now, what I did next was I plugged everything into the formula. So what I'm doing here is I'm plugging in M, C, and delta T, and I'm taking the product of these three numbers, 100 times 4.186 times 4.1, and I get my Q value to be 1,716 joules. Now, this is the heat that the water absorbs. We are not done with this problem. Remember, the whole goal of this problem was not to figure out how much heat the water absorbed, but to determine the specific heat of the metal. So this is kind of like the halfway point. So what are we going to do next? Well, what we'll have to do next is go to the metal side. So we're going to have to figure out what's going on with the metal. So with the metal, we're going to use the same equation again. Only this time we're using the subscript Q of metal, so I know I'm looking at something a little bit different. I'm not looking at the water anymore, now I'm focused on the metal. Now what's interesting about this, Q for the metal is going to be the same Q value for the water, only it's a negative, and this really confuses students sometimes. So where did this Q value come from? Well, it's the same value over here, only it has a negative sign on it. Remember, the water is absorbing heat, so its Q value, its heat, is positive. The metal, however, is releasing heat. So from the viewpoint of the system, which in this case is the metal, it has to be a negative number. So just remember that when you're dealing with a coffee cup calorimeter question like this, your metal is going to have a negative Q value. So I've got negative 1,716 for the Q value. The mass of the metal, again, this isn't a big deal at all. This is something that was given to me in the problem at the beginning. What is the C value? Well, specific heat is the whole purpose of the problem. That's what we're solving for. So we actually don't know that number. So we're going to put a question mark by it. And then again, I have delta T. And this can be a little bit tricky too for students. This is a negative number. So let's talk a little bit about why in the world this number is negative. Well, if you look at the problem, you have to focus on what temperature the metal was at the beginning and what temperature the metal is at the end. Well, at the beginning of the problem, the metal had a temperature of 100 degrees Celsius. At the end of the problem, the metal's temperature was 27.8 degrees Celsius. Whenever you have to find the change in temperature, you take the final temperature minus the initial temperature. So the final temp of the metal was 27.8. The initial temperature of the metal was 100. So 27.8 minus 100, that's what's going to give us this number, this negative 72.2 degrees Celsius. So it's a negative temperature change. Now, how would we put all this together? Well, we're going to use our Q equals MC delta T equation again. We plug in Q, we plug in M, and we plug in delta T, and we solve for C. So you can see here I just did some algebra. I simplified the right side a little bit, and then I took negative 1,716 divided by negative 4,263. Now notice, because I was careful and I was able to give the Q value a negative sign, and I did the delta T correctly and gave it a negative sign, that when you take a negative divided by a negative, you get a positive. This is what you want, because I was able to solve for the value of C, or specific heat. Notice my specific heat is a positive number. Your specific heat, remember, this is the amount of energy it takes to raise the temperature of this substance. it can't be a negative number. You can't use it can't take negative heat to heat something up.